We want to find out what the Laplace transform of sine AT is. So find the Laplace transform of sine AT, where t is the horizontal axis, alright? F of t would be the vertical axis. It's similar to when you have x and y, alright? Or in some cases x and f of x. Just that t in many practical situations is used for the horizontal axis, usually representing time, something changing over time, alright? So we want to find the Laplace transform of sine AT. A is a constant. Now, of course, you know that this means the integral from 0 to infinity of e to the negative st, where s is a constant, and then the function sine AT. Alright? So, here now, let's integrate that. So we have, and by the way, before we do that, I have a table of Laplace transform here. We see, what do they say it is here? Sine AT. This is what we're working towards. A over s squared plus a squared. 1. You will have a table of Laplace transform in the exams and so on. Tables of Laplace transform all around the internet. But we want to see how it is derived before we go on. This is a table I found online by Paul Dawkins, and it's at this website here. Right? So, our sine AT, when we finish, we're supposed to get a over s squared plus a squared. Right? So, let's see what happens. The integral from 0 to infinity of e to the negative st sine AT. Alright, now dt. Now here we want to use integration by parts, because we have integral of a function of t multiplied by another function of t. Now here you remember the formula for integration by parts, and it comes from the product rule in differentiation as well, right? It says the integral of, say, u dv, where u and dv are functions. One of these will be u and the other will be dv, alright? Equal u v minus the integral of v du. Alright? Now, here, let's use e to the negative x. E to the negative st, I mean. E to the negative st as u. So that we'll have the s multiplying the st each time we go through the cycle. So, what we're going to do is let u be equal to e to the negative st, and then dv equals sine AT. Alright? Now, the u then, we have to differentiate this du. This would be the chain rule, which is differentiation by substitution, would give you negative s e to negative st, and then dv. To go from dv to v, you have to integrate. So when you integrate, if you differentiate sine, you get cos. If you differentiate cos, you get minus sine. So you integrate minus sine, you get positive cos. So when you integrate positive sine, you get negative cos. Cos at. But here, you're integrating. Using integration by substitution, you would have this over a. So here, the integral that we have here, let's call it I. The integral, instead of writing all of this over again, I'll just call it I. The integral of u dv equal u, which is e to the negative st, and v, which is sine, v, not sine. This is v here, which is negative cos at over a. Let's put a multiply sign there. It's this time this. It's uv. So the integral of u dv is uv minus the integral of v, which is negative cos at. Let's put the at in bracket. Alright. Over a du. What is du? Du is negative s e to negative st. And that is being integrated with respect to t. Alright, so that's what we have here now. Now, let's see if we can simplify. Oh, by the way, remember, we're going from 0 to infinity. So this is 0 to infinity, 0 to infinity. Alright? So this is equal to, this is going to be negative e to the negative st, but this is the e to the negative st is the same as 1 over e to the positive st. Once you remember your laws of indices, you know that part, right? Times cos at over a, and this is all from 0 to infinity minus what now? This you have here, you have a minus, yeah, second minus and a third minus. 3 negative signs multiply will leave you with a minus sign. Alright, now let's factor out the negative s, no, the s. We already dealt with the signs, the s and then the a under here. These are constants, so we're putting them outside the integral sign, so put them on the left. The integral from 0 to infinity of. Okay, so now we have cos, well, let's put this part first. We have e to the negative st cos at dt. Alright, good. So there we have that. Now, this part goes from 0 to infinity, so let's take care of it. What we're going to have here is negative, let's put this in a bracket, negative, let's, if you look at it, we have the two boundaries, the upper boundaries which is infinity and the lower boundary which is 0. Upper boundary is infinity. So it's 1 over e to the s times infinity. T would be infinity. So e to the infinity, right, multiplied by cos a times infinity is infinity over a, right, minus, then you have a negative. Then you have 1 over e to the, you put in 0 now. 0, s times 0 is 0. That multiplies cos a times 0 is 0 over a. Alright? Then we say minus s over a integral from 0 to infinity of e to the negative st cos at dt. Okay, so what happened on the left here? You see 1 over e to the infinity. E to the infinity is an infinitely large number, and 1 over that is 0. So we have 0 times cos infinity. Now cos does not pass positive 1 or negative 1. So 0 times whatever cos infinity is 0. So all of this part amounts to 0. Alright? So that's 0. Minus negative means you're going to plus here. Cos of 0 is 1. E to the 0 is equal to 1. So it's 1 over 1. So it's 1 times cos of 0 is 1. So it's 1 over a. So this amounts to 1 over a. So 0 plus 1 over a is just 1 over a. So all of this thing comes right down to 1 over a. Alright? Minus s over a integral from 0 to infinity of e to the negative st cosine of at dt. Alright, now this part, you have the integral from 0 to infinity of e to the negative st cos at dt. But the thing is, this is the Laplace transform of cosine, right? It would turn out to be the Laplace transform of cos. But let's see what we can do with this. Let's take this part and integrate it by parts and see what we come up with. Hopefully we'll get something with sine in it, and it could substitute back up here. Alright, so let's make a note of this part. Let's put 3 lines on there to mark it. Alright, I will come back to it. Now, what we have is the integral from 0 to infinity of e to the negative st cos at dt. We're going to use integration by parts. So let u be equal to e to the negative st and dv be equal to cos at. It's a repeat of what we did earlier. Alright, du would be negative s e to negative st, and v would be, when you integrate cos, what you get? When you differentiate sine, you get cos. So when you integrate cos, you get sine. So sine at over a. You'd have to divide by a if you remember your integration by substitution, right? So what we have here is the integral. All right, let's call this, we call the first integral I1. Just to shorten up things, let's call this I2. All right, so what we have here is I2. So here now, I2. That's the integral of all of this. I just call that I2. Right? This is equal to, so the integral of u dv is equal to u, which is e to the negative st, v, which is sine at over a, minus the integral of v, which is sine at over a, du, which is negative s e to negative st dt. All right, remember, we have to bear this in mind. We're going to have to come back to it later on. So this is equal to, now we're going from 0 to infinity. This is from 0 to infinity. So what we have here is 1 over e to the st sine at over a. We're going from 0 to infinity, minus, okay, we have two minuses here, this and this, multiply, so we get a plus here. Let's take this s as a constant outside of the integral sign. It's in red, but I just rewrite it in black. And this as well, it's a integral from 0 to infinity of, this is e to the negative, let's rewrite this in red, e to the negative st sine at dt. All right, now this part we're going to have 1 over e to the infinity times sine a times infinity is infinity over a. But 1 over an infinitely large number is 0. So this part amounts to 0. Minus, then we put in the 0 for our lower boundary. It was infinity upper boundary, 0 for lower boundary. Alright, so let's just write it in black instead of green. We wrote it in green first, but can be. Let's look at it. So what we have is 1 over e to the st. S times t is s times 0 because t is 0. So this amounts to e to the 0, which is 1. Right? This would be e to the 0, you know. But e to the 0 is 1. 1 over 1 is 1. So just write 1 here. Times sine of 0, because sine of a times 0. A times 0 is 0. Sine of 0 over a. But what is sine 0? It is 0. So 1 times 0 is 0. So all of this amounts to 0. Plus s over a integral from 0 to infinity of e to the negative st sine at dt. Now this is the Laplace transform of sine at, right? I was writing it, the at in brackets, but sometime I skipped it out. Right, these at's, just to be consistent, let's put them in bracket. All right. So here now, what we have is this. That 1 over a minus s over a times, so it's 1 over, let's write this in black, 1 over a minus s over a times, now all of this part, now I2 amounts to this, so it amounts to s over a times the integral from 0 to infinity of e to the negative st sine at dt. Now, all of this we were saying is the Laplace transform of at. See that? So, scrolling back up, this is the Laplace transform of sine at equal that. Well, can't scroll up any further. We have to go to the side after this. Now, the thing is, what is this here? The integral from 0 to infinity of e to the negative st sine at is the Laplace transform of sine at. This, you know. So, the Laplace transform of sine at equal 1 over a minus s over a times the Laplace transform of sine at. This is what we're dealing with, right? Now, here, let's move over here and continue the work on this thing, because we run out of scrolling space downwards. Let's draw a line to divide. Let's draw a line to divide the screen and continue working here. All right, so what we have is this. What I'll do, instead of trying to remember everything and rewriting it, I copy all of this and put it up there and work with it. All right, so this is what we had. Now, the Laplace transform of sine at equals 1 over a minus, let's multiply out. This would be s squared over a squared times the Laplace transform of sine at. Now, if we add both sides, add s squared over a squared to both sides, what we have is the Laplace transform of sine at plus s squared over a squared times the Laplace transform of sine at equals 1 over a. So, let's factor out the Laplace transform of sine at. Now we have 1 plus s squared over a squared equals 1 over a. So the Laplace transform of sine AT equals, let's divide. We have 1 over a divided by 1 plus s squared over a squared. Let's see if we can simplify this thing now. What is 1 over s squared over a squared? This is 1 over 1 plus s squared over a squared. Now, if we work with this and draw the line and find the LCM, let me write it larger. 1 plus s squared over a squared. 1 plus s squared over a squared. This one can be written as 1 over 1. What we could do, use common denominators instead of drawing the line and finding the LCM. If you multiply 1 by a squared and multiply 1 by a squared, all of this, is the same one, if you remember your fractions. And we have common denominator. We have an a squared here and an a squared here. Common denominator. So this amounts to a squared over a squared, right? It's the same thing you would get if you draw the line and find the LCM. A squared over a squared. Alright. So this is 1 over a divided by. This now can be written as a squared plus s squared over a squared. Right? Have to remember your fractions, So the Laplace transform of sine AT equals, alright, so when you have this over a fraction, remember what to do. The numerator that is multiplied by the reciprocal of the denominator fraction. So it's a squared over a squared plus s squared. So a into a goes one time, a into a squared goes a time. Is a over a squared plus s squared. Is that what the table said? Let's look back. A over s squared plus a squared. A over, good. It's just that they write s squared first. So let's write that. The Laplace transform of sine AT is equal to a over s squared plus a squared. Alright? Now, when doing Laplace transform, in exam you would already have a table of Laplace transform. So you wouldn't have to go through all of this unless they tell you to derive the Laplace transform of AT. You need to have to do all of this work, right? But normally you wouldn't have to do all of this work. You would have that in the table as well. So I'll see you in the next video, so stay tuned.